Something that's extremely important to be able to do when you're working through a physics course like this, dealing with vectors, is to be able to so-called report vectors, or do this reporting of vectors. In other words, you have to be able to specify what your answer is based on some vector which you might have retrieved in the problem. So let's look at an example here, which I've used in a previous video, but we'll just sort of crank it up one more time here. There's a coordinate system here, and again, say there's some object which has ended up being over here, maybe moving at 10 meters per second at 37 degrees, something like that. So it's just sort of a, however this came out, it's just the physics or the math that happened to come out that something's moving at 10 meters per second, 37 degrees. Could be the result you had, it could be stated in a textbook. But in either case, if you want to report this as a vector now, you have to be very quick and sort of keen about recognizing exactly how you want to report this. Like, say, for instance, you might need the x and y components of this for some various reasons here. And so you need to be very quick at recognizing that the vector here, when you look at it, is always going to be the hypotenuse of a right triangle here. So the vector itself is always going to be the hypotenuse right here. Hypotenuse here. And then the so-called the vector components, there, well, those are always going to be the legs of the vector. So in this particular case over here, if you look very carefully, this component over here, which I'll just sort of label v sub x, is the x component. This component over here, which I'll label v sub y, is the y component. And if you get the right triangle formed properly, in other words, the vector is always the hypotenuse, this part right here, and the vector components are always the legs. There's a leg and there's a leg. The right angle is always going to exist in there, and you should be pretty quick now with your sine and cosine to figure out exactly what v sub x and v sub y are. Now, when I look at this diagram here, I can immediately see that v sub x here is going to be 10 times the cosine of 37, because x here is the angle that's adjacent, is the side that's adjacent to the angle, and cosine involves the adjacent, so that'll be the cosine. Likewise then, v sub y will be 10 times the sine of 37. So two components can immediately be plucked out like that, and if you want to continue and punch it into your calculator here, you'll notice that this number here is going to be 7.9, and this number here is going to be 6. They will carry the same units as the original vector. This will be in meters per second, this will be in meters per second. So the interpretation then is that if something's moving at 10 meters per second at an angle of 37 degrees, again, this is the 37 degree angle in here, then that's equivalent to having 7.9 meters per second along the x-axis and 6 meters per second along the y-axis. And technically, yes, because the v sub x is sort of moving towards the left, which is negative, the v sub x would be negative at minus 7.9 meters per second. Often the minus sign needs to be put in by yourself because it doesn't come out naturally using any of the trigonometric functions there. So looking at this vector sort of pointing up and to the left like that, we're able to come up with the two components. And so one thing that's going to be very important to do then is to be able to always work on this operation no matter what the orientation of the vector is. So here's another example like this. Suppose you're working on a problem, the vector came out like this. Again, I'll just call it some parameter v like this. It could be the 10 or the 20 or whatever, but the question is, can you go in here and identify the two components of this vector? Now the easiest way of doing that always is whenever you see a vector like that, is to draw a little Cartesian coordinate system always along the tail of the vector. So something like this and something like this. And now it might become immediately familiar to you with, oh, I know what's going on now. This would be the angle theta in here, and now I can draw the components in here. This would be the v sub y, and that would be the v sub x over here. So in this case, the trig functions can be used as needed, but you'll notice that the v sub y and the v sub x are very clearly specified now. V sub y would be positive, v sub x would be positive. The sines and cosine can be used as needed. Here's another example. Let's look at the same vector like that, but suppose it looks like it could be the same, and indeed it is, same direction, but if you drew a Cartesian coordinate system on it now, you might be doing this upside down and just have some different thoughts in your head. You could very well identify the x component right here. It would be the v sub x right here, and you could identify this as the v sub y. It'd be sort of exactly the same problem, only now your theta isn't here. There would be your angle in there. You'll get the same answer, but notice the theta over here is exactly 90 minus theta over there. But in either case, the trig and the math and so on will work out just fine because of the way the sine functions work, or the trig functions work. Here's just another example. Here's a vector that points downwards like that. Here's a vector that points straight down like that. Maybe a vector that points straight over like this. And let me do maybe one more, a vector that, say, points downwards like this. So these are all vectors that conceivably come up in any problem you're working on here. A down and to the left, a straight down, a straight left, and a down and to the right. How would you be ready to recognize all the vector components of these three things? Hopefully you can. Again, just draw that Cartesian coordinate system on the tail, and you can immediately see the needed geometry popping up. So there might be an angle, say maybe alpha in here, and you can definitely draw the y component like that, and the x component over like that. So there would be the x component right there, there would be the y component right there, and now you'd be ready to use your sine and cosine to figure out what the x and y components are. This is a vector that's straight downwards like that, so you could just draw a Cartesian coordinate system straight on it like that, and immediately notice that the x component of this vector is going to be 0. It doesn't have a component horizontal at all. It's all straight down. You can just pick that right out. Likewise, this one right here, if I draw a Cartesian coordinate system on top of that, straight horizontal, and the last one sort of oriented down like this, again, a Cartesian coordinate system right on the tail of it would look something like this, where here's the vector straight down like that, and there would be a v sub y. If it was a velocity vector, v sub y like that, and a v sub x like that, and maybe the angle theta is given right in there like that one. And once again, the trigonometric functions can be used to find out exactly what v sub x and v sub y are. The signs are very important on these things here, so I'll just go back one more time through these examples I've given here. In this case here, the x component would be negative and the y component would be negative. Why that? Because this one's pointing this way. The left direction along x is negative, the down direction along y is negative. This one right here that has this component all along the y-axis, this would be a negative y component here. This one over here would be a negative x component, and the direction is pointing in here. Over here, looks like the x component here would be positive because it's pointing to the right, while the y component would be negative because it's pointing down like that. But in either case, the takeaway here is that you should be able to take a vector pointing in any direction, this way, this way, this way, this way, this way, any direction, wrap a Cartesian coordinate system around it, recognize the x, y components, and be able to use sine and cosine to figure out exactly what the x and y components are for the vector.